Welcome to the 18th lecture of this course, and today we will be talking about how do we do the quantization of electromagnetic field and and all the issues that we have discussed in the last two lectures. Here we'll proceed with some gauge fixing. Okay, so after adding this gauge term of del mu a mu equal to del mu a mu square, in the previous lecture we said this is the Lagrangian that we got after two partial integration by parts for the gauge term. This is what the Lagrangian looks like with 1 by xi modified. Xi could be any real number, and with this Lagrangian, this is a part of your homework to find this, but you'll find that pi mu will be something like this over here. Okay, so let me use the highlighter. So here if xi term was not there, or so to say, if the xi is infinity, that's another way to suppress that term, then one would have said that the first term and the second term would have simply cancelled each other for mu equal to 0. Okay, and my Lagrangian would not have a term containing a0 dot, so pi 0 would be 0. But here, since the xi is non-zero, what we see is that our pi 0 is also non-zero apart from pi I. So our field momenta is actually non-zero, and we can do computation with that. And while doing the computation, one can choose different values of the xi, because xi could have been anything. And xi equal to 1 is called the Feynman gauge, and xi equal to 0 is called Landau gauge. It appears over here that xi equal to 0 will make this term go to infinity, but what one means is that you do a computation keeping the symbol psi, and at the end, if the result simplifies for xi equal to 0, then you use that. One is free to choose any value of xi over there. So now if I choose xi equal to 1, which is the Feynman gauge, and most of these computations over in this lecture we will do for xi equal to 1. So when xi equal to 1, the second piece over here, this piece disappears, and we only have this piece which is written over here. Okay, so my pi mu is minus of a dot mu. Now you note this opposite sign. Okay, compare to the Klein-Gordon scalar, where the field, the momenta, was nothing but the phi dot. Okay, so here what I'm getting is with the opposite sign, and that has a lot of consequences, and that is also the cure of the problems that we were having. We just have to be patient and systematically do the computation. In, of course, the Feynman gauge, it can be done in any other gauge. That doesn't really matter. In Feynman gauge, it becomes more transparent exactly what is happening. Okay, now we can write down the canonical commutation relation at equal times for a mu and pi mu, because these two are now when they are elevated to the operators, one can write this commutation relation, and pi 0 is non-zero, so of course I can write it. Okay, so this commutation relation will of course have d3, this delta function. Allow me to correct a little thing over here. It is a minus sign. Okay, so this is delta 3, three-dimensional delta function. Then here mu nu are there, so the g mu nu is the only second order rank tensor we have. I will be there, and an opposite sign sits over here, and this opposite sign is, it's nothing out of the world. Is just that, you see, when we write phi in terms of the a and a daggers, it's the phi and phi dot that has a nice commutation relations. And so if there is a minus sign over here, it's obviously, when I put the phi mu as a minus a dot mu, I expect the minus sign to be on the right hand side as well, such that my commutation between a's and a dagger should be respectable. Okay, so we will have this opposite sign. Now another thing comes is that this opposite sign, even when I put a minus sign over here, the opposite sign appears only when mu is equal to 0, mu and mu equal to 0. It means for a0 and pi 0, now that pi 0 is non-zero, I still have this issue that it comes with the opposite sign in the commutator. Okay, All others are correct sign. If I don't have this minus sign over here, then it will be a0 pi 0 that will have a correct sign, and but all the AIs will have opposite sign. Okay, so here we cannot do much. G mu nu is the only second rank tensor that we have, which is Lorentz invariant, is a Lorentz invariant tensor that we have, or Lorentz covariant tensor, I should say. Now here one has to be careful about the gauge condition. So we just put the del mu a mu whole square equal to 1 by 2 xi times del mu a mu whole square in the Lagrangian, and but I cannot directly say del mu a mu equal to 0, because when we extremize the action, that would be the condition satisfied for the classical dynamics, for getting the classical equation of motion. Okay, but for quantum system one has to be careful. For example, if I apply del mu onto this equation, act with the derivative, then LH left hand side will be 0 if I use the del mu m equal to 0 condition, but the right hand side will not be 0. Okay, so this canonical commutation relation in itself does not directly support this, so one has to be careful about extracting the right information which satisfies the gauge condition. So we will not apply it here itself. So this is the CCR with which equal time commutation relation, and we'll have to be very careful about imposing the gauge conditions. Next we move to what we have for the propagator. So I'm not going to do the calculation for the propagator. In the previous lecture I already hinted that for all the free fields, for the scalar and the fermion, how did we compute the propagator? And then I showed that the operator sitting in between for the gauge field was a projection operator. Now again in the homework you have seen that in the presence of this gauge fixing term, that guy is not a projection operator and can be inverted. Okay, so in the homework you have seen that this P mu nu for this case that can be is invertible, and the inverse is related to the photon propagator, which happen to be this quantity. Okay, I by k square plus I epsilon, and this sitting over here in the square bracket is the inverse of P mu nu. Okay, and here as I said P mu nu is xi dependent, so here also there is a xi dependence. Now when I put xi equal to 1, you see very nicely this second piece disappears, and for the Feynman gauge I have this nice simple looking propagator over here. Okay, but when I put xi equal to 0, now it is possible because it's sitting in a numerator, I'll get the Landau case, and here also this sometimes simplifies the computation, because this G mu nu minus K mu Q nu by K square is a projection operator that is sitting in the numerator. Okay, so sometimes it is useful. So we will use this as and when needed, but for this lecture we will work with xi equal to 1. This is the case when pi mu is equal to a dot mu, as we said in the previous slide. Okay, so this is the condition with which we'll work for rest of this lecture. So given this canonical commutation relations and all this, let's say how do I do a mode decomposition of a mu x? So it is a mu x will be standard d3k by 2 pi q 1 by square root of ek twice ek, then sum over r equal to 0 to 3 epsilon r mu. So epsilon mu is a vector because the left hand side is a vector, but how many of them it can be? Okay, so for a given a mu I have to span the entire 4-dimensional space that it has. Okay, 4 degrees of freedom that we have, so we have to be carefully take care of all of that. So here we see that E mu is a vector, the Lorentz vector, but R is what labels the degrees of freedom. Okay, mu doesn't label, but R labels. So for each degree of freedom, so E mu R K and ARK is the corresponding annihilation operator, and this is just a wave factor, and here the corresponding Hermitian conjugate will appear with A Diagas and epsilon mu R star, and R ranges from 0 to 3 exactly like mu. Okay, and I have this A mu is a real field, that's why it is A and A Diagar that is appearing. But if I just look at the first piece, this is a standard way to define the A mu plus and the A mu minus. A mu plus has only the lowering operator, and A mu minus only have the creation operator. This is only the annihilation operator. Okay, and here we see that E mu epsilon mu r are the four vectors which can be written in this manner. So E0, so epsilon 0 mu is a vector which is time-like, and all other vectors 1, 2, and 3 are space-like. So 1 is pointing in x direction, 2 is pointing in y direction, 3 is pointing in the z direction. Now, given this choice, if I just contract, so here is another this very important. These are written by considering this relation where ER mu and ES mu star is nothing but eta RS. Okay, and where eta RS is nothing but just diagonal 1 minus 1 minus 1 minus 1. Okay, so this is the normalization that one is using, and if I contract this thing with eta RS times epsilon mu, the R and S coordinates, the R and S are contracted, so what I will get is G mu. If you use exact this representation, this is what you'll get. So we'll work with these notations. Okay, so given this is what we'll use to do the commutation relation computation. So A is here. When you compute A dot, then the EK part, because X is the 4 vector product over here, so the time is sitting over there. So the time derivative over here will bring appropriate changes to this expression, and then we use this canonical commutation relation. We expand it to get this guy on the right hand side and use all these relations over here. Okay, then what we will get, again, apology, here it should have the second piece. Second piece is a star all the time. Okay, so this is the relation you will have. Even without star it makes sense because here nothing is complex. Okay, but in general we should write the expressions correctly, because eventually we will have epsilon 1 and epsilon 2, a complex conjugated combination is what we are going to put over there. That will be left circular and right circular polarized. This is like a linear polarized basis vector. Now if we put these expression in the equal time commutation relation, then what we find after doing computation, which I'm not showing over here, is similar to finding the Hamiltonian and all this stuff. So what you will get is this particular expression. Okay, and again we note the opposite sign. Okay? It's minus of eta RS. Okay, it means it is opposite only for r equal to 0 and s equal to 0 case. For when r is not equal to s, of course this commutation is 0, and of course a dagger with a dagger and a with a commute, so those commutators are 0 also. These are only non-zero commutators with when r is equal to s, and whenever r and s equal to 0, then it has opposite sign, otherwise it's a correct sign. So 0 remains a bone of contention. Okay, so we will see what is the meaning of this, and these are all related, that we are choosing the conventions everywhere wherever we need it to, is such that I have no option but to have something with opposite sign, and I'm only choosing the temporal guy with opposite sign. I made the choice in the very beginning by writing the this commutation relation here, the equal time commutation relation, and that simply carries over to this place where a and a dagger also has negative opposite sign for 0, 0 case. What does it mean? What implication does it have? For which to understand that, we'll look at how we define the physical states. So physical states are defined, especially the vacuum is defined, physical vacuum is defined by a state which is annihilated by all of this AR case. Okay, for all k and all r. And also we define single particle state to be one which is like up to a proportionality constant. I'm not writing the proportionality constant for simplicity. So this single particle state with momentum k and spin indexed r is just AR dagger k acting on vacuum. Okay, now if I have to find the overlap of this state with some other like kr with k prime s, then what you do is just, I'm using this proportionality over here, and so this guy is as dagger k prime, and this is ark on the left hand side. So this particular overlap we'll have. Now we know that using this commutation relation, okay, and the fact that this guy in the reverse order is basically 0, so I can just simply subtract the this operator in the reverse order to get me this commutator, and this commutator is nothing but this number, and then 0 and 0 just gives me 1. So this is my, so to say, this overlap of the state. Okay, an important thing to note over here, that for the case of k equal to k prime, I have a delta function peak. That's a separate issue, but let's just say delta function still is a positive function. It's always positive, never negative. But when r is equal to s equal to 0, okay, here what I have is that this state has negative norm. The norm of the state is negative, and I cannot have a state of any physical state whose norm is negative. Okay, so my vacuum is fine, appears, I cannot change the definition of my vacuum. This is how I want my vacuum to define. This is how I want my single particle state to be defined. But still I'm getting a negative norm state, is because my commutator here has the opposite sign. Okay, so this negative, so it appears this negative norm will lead to some kind of cancellation, because in the computation you find the overlap of one wave function with another, and if we have negative norm states appearing, then they will cancel something else that was positive in the computation. So we expect over here that the negative norm, this particular negative norm, will lead to some cancellation, and the physical observables that one is expected to have, any physical observable that we are looking at, that are expected to have contribution only from the remaining degrees of freedom. Okay, and that is after applying this gauge condition. We have not applied any gauge condition over here. Okay, so we'll see that hopefully this cancellation should happen, and actually gauge condition does exactly that, and this is called the Gupta-Bleuler condition. And what it describes is that instead of saying that del mu mu equal to 0, you say that the matrix element of del mu mu is equal to 0. That I can demand. I could not have demanded del mu mu equal to 0, because demanding that would have said that the CCR is not compatible, because the left hand side is 0, right hand side is no. So I have to drop the CCR if I want to keep the gauge condition, but I want to, for quantization, I want to keep this canonical commutation relation. So I will rather drop that, I choose to drop the enforcing the gauge condition at that level. But in any quantum system, this has to satisfy the gauge condition. So all I need to ask is that the matrix element of this operator del mu mu must be 0 for all physical state psi. Okay, so we know that for vacuum, del mu mu dagger, if I just write del mu mu plus has only, so if you remember, mu is written in terms of mu plus and mu minus, and mu plus has a's and epsilons, and mu minus has a daggers and epsilon stars. So del mu mu plus will still have a's, and a's acting on 0 is 0 according to my definition of this vacuum. But when it's acted upon by a dagger, it is not equal to 0. But that doesn't matter, because the dagger of this particular equation would amount to vacuum on the left hand side acted upon by del mu mu minus equal to 0. By combining these two, I can say vacuum expectation value of del mu mu is 0, because this has two terms, and one term is scaling on the right and other term is scaling on the left. So that basically implies that vacuum is a physical state. It does satisfy this Gupta-Bleuler condition, that the gauge condition has to be satisfied at the level of matrix elements. Okay, now it is the way we did the computation is pretty clear that between any two other states psi, if I have to demand that del mu mu psi matrix element between these two states is 0, that is similar to demanding the del mu mu plus acting on psi equal to 0. Because if this act on right hand side, okay, then the dagger of this will act on left hand side. So del mu mu is nothing but this and plus its dagger. Okay, so one acts on the right hand side giving me 0, and dagger acting on the left hand side will give me 0. So this condition, satisfying this condition, is same as asking for this condition is 1-to-1 correspondence, That's why it is implies and implied by. So I can simply demand this condition, which is del mu a mu dagger, okay, acting on some state is 0. So let's first compute this operator. What does it look like? And we note that it is a Lorentz invariant operator. Okay, so when I act by del mu, the del mu acts on the only position the x appears is this exponential ik dot x, and that gives me a minus I, which is sitting over here, okay, and a k mu, which is sitting over here, and the summation from r equal to 0 to r equal to 3 as it was earlier, and all the factors are sitting over there. A k mu epsilon mu appears with the ar sitting over there. Now, since it is a Lorentz invariant quantity, this particular operator, I can choose any basis for that. Okay, so I choose a basis where the momentum is pointing in z direction, and with regard to this particular choice, these choices of epsilon vector in this page, in page 2, makes sense. Otherwise it won't. Okay, so otherwise I have to have suitable choices over there, appropriately rotated. So so here k mu is ek 0 0 ek, so it is like no component in x and y direction and component in z direction only, and of course energy component is sitting there. So this is my k mu. Now of course k mu epsilon 1 mu is 0 because epsilon 1 mu is only in the x direction, epsilon 2 mu is only in the y direction, so those things are 0. K mu epsilon 0 mu is E, that's this energy first component, and k mu epsilon 3 mu is minus E. Okay, so when I put these expressions over here, so what I get is minus I, this all these factors, then ek I took common, and what I get is a0k minus a3k times exponential ik dot x. So this is the definition of my operator. So when I say that del mu a mu plus acting on psi equal to 0, that can be achieved for every position x and every momentum x, every momentum k, if and only if I say that for all momentum k, a0k acting on psi minus a3k acting on psi is equal to 0 for all momentum. If I demand that, then I will have this condition satisfied. My gauge condition will be respected. Okay, now this is what the cancellation we were talking about. The gauge condition says that your 0th component and the third component cancel each other. Now let's go back to my definition of these epsilons. What are these corresponding vectors? So you see, epsilon 0 is a vector which has no component in the xyz plane, xyz direction. Okay, if I perform any rotation in xyz, it is not affected by it. So E0 mu is called scalar. Maybe I should write it here. So this is scalar. This is in parallel to the momentum because my momentum was in z direction. So this is longitudinal, and these two are transverse. Okay, so what is happening is that my scalar polarization, which was a problematic guy, all the a zeros and pi zeros, which were giving always the opposite sign, that cancels the longitudinal degrees of freedom. Remember that for any spin 1 particle, because photon is going to be spin 1 particle has 3 degrees of freedom. So forget about the scalar. Ideally we should have the 2 transverse and 1 longitudinal, but the way this theory is written in a gauge invariant and Lorentz invariant way for a massless case, what happens is that the so-called scalar degrees of freedom cancels out the longitudinal degree of freedom. Okay, this is what was predicted over here, the negative norms that were supposed to do, and here this is exactly what is shown, that my gauge condition basically amounts to saying that my scalar and the longitudinal component cancel each other. But this is happening at any state level. They acting on the state itself is 0. Okay, now if I have to find something else, okay, like say first of all, if I have to have a normal ordered Hamiltonian starting from the size and all these things and using all the relations, This is also part of your homework. Sorry, this is not part of your homework. Finding the Hamiltonian in terms of fields and the momentum was part of your homework. Okay. So, but here, if you follow the same step as for the scalar in your previous course, you'll find the expression for Hamiltonian, which will be like this, where A are Dagger and AS will be there, and minus eta RS you are contracted with. Okay, so if I write it in the component form, you'll have r equal to 1 to r equal to 3 with a positive sign, A Dagger A, and the temporal part, the 0, it comes with the opposite sign. Okay, so this is how your Hamiltonian would look like, and again it is minus eta RS that is coming everywhere. So if I had to take a vacuum, not vacuum, but any matrix element, mind it, I'm not saying psi and psi on both sides, it is psi and psi prime. Okay, to any two physical states, if I throw at this Hamiltonian and say, let me take the expectation value of this Hamiltonian. And what I do is that just for simplicity, I only write the operators over here. So there will be a term, and so all these integrals and prefactors are not written. So there will be a term which says psi bar A3 Dagger A3 psi for each k, each value of the momentum over here, minus psi prime A Dagger A0 A0 psi, plus you have the similar term for A1s and A2s. Okay, so this is what I'm not worried about at the moment. Now let's look at this term. If I say A0 acting on psi, because I don't know what psi could be any state. It's not that A0 acting on psi is 0. Yeah, if psi 0 is vacuum, then yes, otherwise it is not. So A0 acting on psi, if I denote by phi, then by my gauge condition, A3 acting on psi is also phi. Okay, and if A0 acting on psi prime is some chi, because psi prime could be any other state, so chi is some other state, then similarly A3 acting on psi prime is some same state chi. So what you are getting over here is that chi overlap with psi minus chi overlap with psi, so these two cancel. It's exactly cancel. Okay, so what I'm left with is just this term. So the psi bar H psi has contribution from the transverse modes only from any physical state. So whenever you take the vacuum expectation value between any two physical states, you have contribution only coming from the transverse degrees of freedom, and these 2 degrees of freedom simply disappears. So the Hamiltonian is effectively describing 2 transverse degrees of freedom, because the longitudinal would never appear as long as it is satisfying the gauge condition. Now if you are looking for unphysical states, okay, then of course they will give some contribution, but they are not the physical state. The physical state has to be projected out using this gauge condition or the Gupta-Blauer condition. All the physical state must satisfy this Gupta-Blauer condition. Okay, so with this condition satisfied, this is how we, so to say, put the constraint on the phase space. The phase space of classical mechanics is the Hilbert space in the quantum mechanics, and this is a condition I am putting on the Hilbert space. Okay, so and this is the only way I can do. I cannot directly put the constraint onto this constraint. I cannot directly use on the fields. That's why we started with adding this term to the Lagrangian, such that the gauge symmetry is broken. That's another way to say I'm choosing a gauge, and so I can find a pi 0 which is non-zero. I can do all this analysis and then quantize it, and quantized theories still have all the pathologies, and those pathologies is solved by this condition, this one single condition. Okay, so which leads to a cancellation of the scalar quantization, scalar polarization with the longitudinal polarization. Okay, so with this I finished this particular lecture. In the next lecture onwards, we will start with the non-abelian gauge theories and how to do some computation in that. And quantization of the non-abelian gauge theory would also proceed very similar, because we will show that non-abelian gauge theory is basically many copies, many independent copies of this U1 electromagnetism, and so the same conditioning, same kind of concept will be carried over. However, when it comes to actually doing the quantization, I would actually prefer path integral formalism, and here also for electromagnetic theory I will do a path integral quantization of this. I feel more comfortable with that, and there the concepts are easy to invoke, and you can get all these results by following a simple set of rules in the path integrals formulas. Okay, so with this I stop my lecture over here. We'll see you in the next lecture.